Yeah, in this video, I'm going to discuss about the shape of sulfur tetrachloride, tetrafluoride, according to this VSEPR theory, on the basis of this VSEPR theory. This has pulled out from the degree first semester syllabus, that is Chemical Bonding, Chapter 10. The whole of this VSEPR theory has been described, has been uploaded on my YouTube channel, uh, the description of which is given in the description box below. Yes, you can go through it, and if you like it, please do like, share, and subscribe my channel. Let's connect to the topic. When we discuss the shape of the sulfur uh, tetrafluoride, that is SF4, uh, according to this valence shell, VSEPR theory, valence shell electron pair repulsion theory. So the theory is totally based on the presence of valence electrons and the repulsions in between these electrons in the valence shell. That means the repulsions in between the lone pair or the bond pair of electrons which are present in the valence shell. So the name this valence shell electron pair repulsion theory. So the theory is totally based on the repulsions in between the valence electrons which are present in the outermost shell. Yes, when we come to this sulfur tetrafluoride, that means SO4, this sulfur, its atomic number is 16, so its electronic configuration will be 1s2, 2s2, 2p6, 3s2, and 3p4, right? Yes, so outermost electronic configuration as the valence electrons are 6 valence electrons. And steric number of this, so is, I've already said this in my previous video, is equal to, that means this number indicates the presence of the orbitals in the outermost shell. So, or the valence shell, that is equal to half into the number of electrons on the central atom or the valence electrons on the central atom plus the number of the bonds, that means the single bonds which are attached to this central atom, plus or minus the charge. If there is a positive charge on the molecule, just subtract it, and if there is a negative charge, just add it to the this number. Yes, so now in this particular molecule, that is SF4, central atom is sulfur because it's only 1 in number, and fluorines are 4 in number. So the one which is least in number or which is having the more atomic number or which is least electronegative can be selected as a central atom. So in this case, a sulfur is the central atom. So this is half into the number of valence electrons on the central atom is 6, and the number of the bonds is 4 because it is connected to 4 fluorines here. It is 4, which is equal to half into 10, which is nothing but 5 here. So this 5, this number, which means that on the central atom fluorine, it is connected to, it has 5 orbitals around this sulfur. So it is connected to 4 fluorines and 1 is the lone pair of electrons. This is because, see, the sulfur, the number of valence electrons are 6, 4 are connected to fluorines by means of bonding, covalent bond. So this is 4 fluorines and 1 other is a lone pair. That means 2 electrons are 2 electrons. So 4 plus 2 is 6. So out of the 6 electrons, 4 are involved in the formation of covalent bonds with 4 fluorine atoms, and 2 electrons remains as a lone pair on this central sulfur atom. Now the question arises how these lone pairs and bond pairs are arranged around this central atom. So these fluorines which are connected by means of covalent bonds, the electrons which are involved in this are called as bond pairs, and which remains as a 2 electrons lonely is called as a lone pair. So how these are arranged around the central atom? Yeah, let's look at this now. Yeah. Now coming to the geometry of this SF4, this, yes, this is SF4, right? Uh, I said the steric number is 4, which means that the presence of 4 bond pairs and 1 lone pair, right? Around this central sulfur atom. So the geometry is, if it is 5, the hybridization is, it is sp3d. 1, 2, 3, 4, 5. Okay. The hybridization is sp3d. The geometry is trigonal bipyramidal. Yes, I'll explain to you what is this geometry. So the geometry is, when the steric number is 5, it is trigonal bipyramidal, which means that around this central atom, 3 bonds are in one plane and the other 2 bonds are above and below the plane of this triangle. So this looked like a pyramid above and pyramid below. So the name trigonal bipyramidal, it's looking like 2 pyramids above and plane of below the plane of this triangle. So the name trigonal bipyramidal. And I've already said that there is one lone pair on this central atom, that is sulfur. So this is the general geometry when the hybridization is sp3d. I mean, hybridization is sp3d. That means the steric number is, 5. Now, coming to this SF4, the geometry is trigonal bipyramidal. Yes, it is bipyramidal because the steric number is 5 here, and we know that 4 bond pairs and 1 lone pair around this central sulfur atom now. So, out of this 4 bond pairs and 1 lone pair, in the general structure of this trigonal bipyramidal, the bonds which are above and below the plane of this triangle are called as axial bonds or apical bonds. There are 2 axial bonds in this case, and which are in the plane of this triangle, these 3 are called as equatorial bonds. So in general, the axial bonds are longer than that of these equatorial bonds. So now the question arises, where this lone pair is to be placed around the central sulfur atom, whether it is to be placed at the equatorial position or the axial position. So it is placed in such a way that the molecule gets a minimum, will have the minimum repulsion in between these bond pairs and the lone pairs of electrons. So the total, I've said that the valence shell electron pair repulsion theory is totally based on the repulsion in between these lone pairs and bond pairs of electrons. So lone pairs and bond pairs of electrons. So the lone pairs are placed around the central atom in such a way that it will face the minimum repulsion in between these lone pairs and bond pairs. So these lone pairs can be placed now. Yeah, these 2 are axial bonds and these 3 are equatorial bonds. It can be placed at this equatorial position or it can be placed in this axial position. So yeah, coming back to this, if suppose, as in structure A, if this is placed, this lone pair of electrons are placed in axial position, this is an axial position here. So if it is placed in the axial position here, these 3 are equatorial positions. So 3 equatorial positions, 3 fluorines, and 1 axial position is occupied by fluorine and other axial position is occupied by this lone pair of electrons in this structure A. So if suppose the lone pair of electrons are placed in the axial position, as you see in this figure A, these are 120 degrees. I forgot to tell you this. So the angle in between these 3 fluorines, which are arranged in the triangular manner in this particular plane, is 120, and the angle in between this axial and this equatorial is 90 degrees. So if the lone pairs are placed in this axial position, then it will face 3 lone pair bond pair repulsions that is, which are at 90 degrees. We know that the 120 degrees repulsion is more than 90 degrees repulsion, and when we place this at, I'm sorry, this is 120 degrees repulsions is less than 90 degrees. That means if the electrons are placed at the lone pair of electrons are placed at the 90 degrees position, then they will face the maximum repulsion when compared to the electrons which are placed at the 120 degrees. So now when we are placing this lone pair of electrons at 90 degrees position, uh, it will face the repulsions between lone pair and this bond pair. So 1, 2, 3. So it will have 3 lone pair bond pair repulsions in this case, that is 90 degrees repulsions. And now in this particular case, if this lone pair is placed at the equatorial position as we see in this figure B, then in this case it will face only 2 lone pair bond pair repulsions at 90 degrees. So this is the fluorine at 90 degrees to this lone pair now. So these two fluorines which are placed at the eggshell position are at 90 degrees to this equatorial position of lone pairs. So it will have 2 lone pair bond pair repulsions, that is of 90 degrees. So as this is facing less repulsion when compared to that of the figure A, so the figure B is more stable when compared to that of this figure A. Because of the minimum repulsion here in this particular figure B, it will face the minimum repulsion when compared to that of the figure A. We know that if there is a minimum repulsion, the structure with minimum repulsion or the shape with the minimum repulsion is the more stable when compared to the shape with uh, more repulsion. So when we look at these two structures, depending upon these two factors, that is the lone pair bond pair repulsions and the presence of the lone pairs at 90 degrees or 120 degrees, now we came to the conclusion that the structure with the lone pairs at the equatorial position will face less repulsion when compared to the structure with this lone pairs at the eggshell position. So SF4 will try to have the electrons, that means the lone pair of electrons at the equatorial position, because it is having less repulsion when compared to that of this when these electrons are placed at this eggshell position. So figure B is more stable when compared to that of this figure A because of the minimum repulsions. It is more stable when compared to that of this figure A. So now so now uh, now this looking at the structure now, this will have lone pair of electrons at this equatorial position here, and it will have fluorines at eggshell positions, 2 at eggshell positions and 2 at equatorial positions. So this is similar to this structure where these two, when we see this, are eggshell. These two fluorines are, when encircling these, are eggshell. So I'll label them, and these two are equatorial here. So I'll change the color. Yes, this is equatorial and this is equatorial. These two fluorines are equatorial here. So I said already that the eggshell bonds are little longer when compared to that of these equatorial bonds. So this is these eggshell bonds are 164.6 pm, which is little longer than this equatorial bonds, which is 154.5 pm. And the angle now, because of the repulsions in between these lone pairs and bond pairs, because lone pair bond pair repulsion is more than bond pair repulsion here, and lone pair is more than lone pair bond pair, and which is more than bond pair repulsions, because this lone pair which is present on this central S atom totally belongs to the sulfur atom. Now it's try to occupy more space around this central sulfur atom. So it will try to repel these bond pairs of electrons in its bond pair. As a result, these are the angle in between this, which is supposed to be 120 here, in this case, in between these two uh, equatorial fluorines, which supposed to be 120 here. Now it's little reduced to 101.6. And the angle in between these two axial fluorine, which is supposed to be 180 linear, now it is reduced to 173.1. As a result of this, now this particular structure, when we tilt the structure like this a little, now it will be in the shape of this seesaw shape. This is fluorine, this is fluorine, and this is one fluorine. Uh, so these two are supposed to be these two equatorial bonds, and these two are supposed to be axial bonds, and there is a lone pair which is present on this central sulfur atom in one of the equatorial positions. So this is the structure of SF4, which is nothing but seesaw, where you can say that the central because of the presence of this lone pair on the central sulfur atom, there is a repulsion in between this lone pair and bond pair of electrons. As a result, the angle is slightly reduced and the shape is supposed to be seesaw. So in trigonal bipyramidal geometry with the steric number of 5, the geometry is, we can say that the geometry is trigonal bipyramidal. Yes, and the shape of this totally depends on only the bond pair of electrons. So as I said, the shape, when we are taking the shape of the molecule, we don't consider this lone pair of electrons, just ignore this lone pair of electrons. If we ignore this lone pair of electrons, it's looked like a seesaw. So the shape of this is seesaw, while geometry is trigonal bipyramidal geometry. So the geometry is trigonal bipyramidal, and if there is one lone pair of electrons in this, the shape will be seesaw shape. So the geometry will be, the shape will be the geometry of the molecule if there are no lone pairs, but as there is one lone pair of electrons which are present in this SF4 molecule, the shape of the molecule is seesaw here. Yes. So while this is a very important point to remember that while regarding the shape of the molecule, according to the VSEPR theory, the lone pair of electrons on the central atom has to be ignored. But while taking the geometry, both lone pairs and bond pairs of molecules have, bond pairs of electrons on the central atom have to be considered while taking the geometry. But while taking the shape of the molecule, the lone pairs are ignored. It depends totally on the bond pair of electrons. So this is the shape of SF4 according to the VSEPR theory.